All right, we have one last topic to wrap up chapter 3. So this is a definition of a subspace. And so we have a vector space V, a field F, and then W is called a subspace of V if two things hold. First, W is a subset of V, and second, W is a vector space. Okay, so we have a large vector space V, and then we have W contained in V, and it's a vector space also. That's when we call it a subspace. And this is a useful idea because of the following theorem. So the theorem says if you have a vector space V and W is a subset, then it's a subspace if two things hold, if it's closed under vector addition and closed under scalar multiplication, and that's it. So this is a pretty powerful result, and it's sometimes called a subspace test. And what it's telling you is you know that W is a vector space only if those two properties hold, closed under addition, closed under scalar multiplication, when you are in this setting of being a subset of a larger vector space. We've seen something very similar to this in chapter 2 with rings and subrings. And so part of your homework is going to be thinking through this theorem and how it works. Why do we know all of the other vector space properties just based on vector addition, scalar multiplication here? What is the power that's coming in to let us conclude that W is a vector space? But for right now, we're just going to look at some examples. And so for our first couple examples, our field of scalars is going to be Q, okay? And we actually have a bunch of vector spaces and subspaces. So Q adjoin root 2 is a subspace of Q adjoin root 2 root 3. And Q adjoin root 3 is a subspace of Q adjoin root 2 root 3. And Q adjoin root 6 is a subspace of the same thing. Okay? So those are all subspaces. We have the larger vector space. In this context, that's our Q adjoin root 2 root 3. That has more elements in it. And we're just taking some sub-collection of those elements. All right. We can also say, let's say our field of scalars is Q. We can say that Q is a vector space, and it's a subspace of R as vector space over Q. Okay, and R is a subspace of C. So those are both vector spaces with scalars from Q, and R is a subspace of C, the complex numbers. All right, and then one that's a little bit different, and where we're really going to use this theorem and prove something, is a set called UNR. And actually, I'm going to make it U2R. U sub 2R. This is the set of all two upper triangular matrices with real coefficients. All right, so what do I mean by upper triangular? So upper triangular means anything that's not in the upper triangle of the matrix will have 0 in that position. So if I take any matrix and I sort of look at that main diagonal, that top left to bottom right diagonal, that can be non-zero numbers, and anything above it can be non-zero numbers, but everything below that main diagonal has to be 0. So those are called upper triangular matrices. A, B, and C are all real numbers, any real numbers you want. All right, so this is a subset, so U2R is a subset of M2R, which was a vector space over R. All right, and so to say that this is a subset, we need to check two things. So is U2R closed under addition and scalar multiplication? And I should note that times is talking about scalar multiplication, not multiplying the matrices. All right, so let's check closed under addition. So if I take two elements from U2R, let's call them A, B, 0, C, and D, E, 0, F. Those are two arbitrary elements of U2R. So I want to know, how do I add them? And when I add them, do I get back something that's in the same form? So if I add these two matrices, I add component-wise. So I get an A plus D, a B plus E, a 0 plus 0, and a C plus F. And the key thing here is to notice that that equals 0. So this guy, A plus D, B plus E, 0, C plus F, is in U2R. Sorry, I got squeezed in there. All right, and so that is in the set, and so it's closed under addition. So U2R is closed under addition. All right, how about scalar multiplication? All right, so there I'm going to take, like above, I'm going to take AB 0C is in U2R. And let's let R be any element of the real numbers. And what I'm asking is R times AB0C R? And the answer here is yes, RAB0C is equal to RA RB0RC. And again, I'm looking at that 0 right there and saying the rest of those answers are whatever real numbers you want. And so this is in U2R. So U2R is closed under scalar multiplication. All right, and what it means to be able to say that U2R is a subspace of M2R, and so U2R is a vector space. All right, so one more little thing here. I want you to think about, if I describe my U2R as the set of all A, B, 0, C, where A and B and C are in R, are real numbers. What's a basis for it? So could you take that description there and come up with a basis of vectors? And remember, our vectors are matrices, and I don't know how many you'll need. So how many of those would you need? What would they look like? And once you know how many you need, can you tell me how big it is? So I'm going to leave this for you to think about, and there will be an assignment that's similar to this, not with upper triangular matrices, but with a different class of matrices, where you'll prove that it's a subspace, and then you'll be asked to think up a basis. So spend some time thinking about this and post if you have questions or thoughts.